Welcome to this lecture on the principles of immunology. Today, we are going to explore the fascinating world of innate immunity defensive barriers. Imagine your body as a grand fortress. Before any invading pathogen can even encounter your specialized immune cells, they must first breach your body's frontline defenses. Understanding these barriers is the very first step in mastering immunology, as they are what keep us alive in a world teeming with microscopic threats. Now that we know we are looking at the body's frontline defenses, let us start with the physical barriers. Think of your body as a beautiful castle filled with treasure. Outside, millions of tiny invaders, like bacteria, viruses, and fungi, are constantly trying to break in. The very first thing they hit is not an elite army, but massive, impenetrable stone walls. In your body, these walls do not care what kind of invader is attacking. Their only job is to stand tall and block absolutely everything from entering. They work silently, every single second of your life, to keep you safe. Building on that castle analogy, let us look at the actual anatomical structures that make up these walls. The primary component is the intact epidermis of your skin. It is made of tightly packed, keratinized epithelial cells that are highly resistant to any microbial penetration. But what about the openings in our fortress? The respiratory, gastrointestinal, and urogenital tracts are lined with mucous membranes. These membranes secrete a thick, viscous mucus that acts like sticky mud, physically trapping incoming microbes before they can reach vulnerable internal tissues. Trapping the invaders is only half the battle. Now we must expel them. This brings us to mechanical clearance processes. Once pathogens are stuck in the mucus, the body uses mechanical actions to physically throw them out. In your lungs, a system called the mucociliary escalator constantly sweeps mucus upward and outward. We also use forceful actions like coughing and sneezing to eject invaders rapidly. Even the simple acts of crying or urinating provide a flushing action that washes away microbes. Without these physical barriers, our internal organs would be instantly overwhelmed. To truly appreciate how these physical barriers work, we can look at them through the lens of mathematics. This formula models the mechanical clearance of pathogens by the mucociliary escalator using exponential decay. Let us break down the symbols. N of T represents the number of pathogens still remaining in the respiratory tract at a given time. N0 is the initial number of pathogens that were inhaled. The constant E is the base of the natural logarithm. The variable K is the clearance rate constant, which depends on how fast your cilia are beating. Finally, T is the time elapsed. Notice that if the clearance rate K increases, the number of remaining pathogens decreases much more rapidly, meaning your body clears the infection faster. Now that we have our formula, let us see it in action with a concrete example. Imagine a person inhales a dust particle carrying an initial load of 10,000 bacteria. The mucociliary escalator clears them at a steady rate constant of 0.5 per hour. We want to find how many bacteria remain after 2 hours. We substitute 10,000 for N0, 0.5 for K, and 2 for T. Multiplying the exponent values gives us -1. The value of e to the power of -1 is approximately 0.3678. Multiplying this by 10,000 gives us 3,678. This means the physical barrier successfully removed over 6,000 bacteria in just 2 hours without even triggering an inflammatory response. Let us visualize the incredible mechanical clearance we just calculated. In this diagram, you are looking at the lining of the respiratory tract. At the bottom, we have the tightly packed epithelial cells, which form the physical wall. Projecting from these cells are the cilia, those tiny hair-like structures. Above them is the thick mucus layer, where the invading pathogens are trapped. Notice the arrows indicating the movement. The cilia are constantly beating in a coordinated rhythm, pushing the mucus and the trapped bacteria upward and out of the lungs. This diagram perfectly illustrates how the body maintains a sterile internal environment by literally sweeping the danger away. So, we have seen how physical barriers block and sweep away threats. But what if an invader somehow manages to bypass those physical walls? They immediately fall into a metaphorical moat filled with boiling acid and hidden traps. These are your chemical and physiological barriers. They are invisible defenses designed to create an incredibly hostile environment for any microbe trying to survive. Imagine trying to swim in a pool of stomach acid. These defenses ensure that even if bacteria get past the physical blockades, they will find it nearly impossible to grow, multiply, or even survive inside you. Diving deeper into this hostile environment, let us examine the specific physiological and chemical mechanisms at play. Physiological barriers include systemic changes in the body, such as temperature. When you get a fever, your body is actively raising its temperature to inhibit the growth of temperature-sensitive microbes. On the chemical side, we rely heavily on extreme pH levels. The gastric juices in your stomach are highly acidic, as is the sebum secreted on the surface of your skin. If we did not have stomach acid, every meal would introduce massive colonies of bacteria directly into our vulnerable intestines. Beyond just acid and heat, this hostile environment is also filled with active chemical weapons. The body secretes various antimicrobial proteins that act as localized sterilization systems. For example, your tears and saliva contain an enzyme called lysozyme. Lysozyme specifically hunts down bacteria and cleaves the peptidoglycan layer of their cell walls, effectively dissolving their protective outer shell. Additionally, your body produces defensins. These are small, highly potent peptides that literally punch lethal holes into microbial cell membranes, destroying them instantly on contact. They neutralize threats before the adaptive immune system even realizes there is a problem. To understand just how powerful these chemical weapons are, we need a way to measure them. In immunology, we quantify the effectiveness of a chemical barrier using the log reduction formula. Let us look at the variables. L represents the log reduction, which standardizes how effective the barrier is at killing pathogens. And 0 is the initial number of viable bacteria present before they hit the chemical barrier. And F is the final number of bacteria that actually manage to survive. By dividing the initial population by the surviving population and taking the base 10 logarithm, we turn millions of dead cells into a simple readable number. As the number of surviving bacteria decreases, the log reduction increases, indicating a stronger defense. Let us apply this formula to a real-world scenario involving stomach acid. Imagine a person eats spoiled food containing 1 million salmonella bacteria. After 1 hour in the highly acidic stomach, which has a pH of around 2, only 100 bacteria survive to reach the intestines. We want to find the log reduction. We place our initial load of 1 million in the numerator and the surviving load of 100 in the denominator. Dividing 1 million by 100 gives us 10,000. Now we ask, 10 raised to what power equals 10,000? The answer is 4. This exactly 4 log reduction means that 99.99% of the harmful bacteria were destroyed. This proves how incredibly effective physiological pH is at preventing massive bacterial invasions. Let us look at a visual representation of these chemical barriers destroying pathogens. On the left side of this diagram, you see the stomach environment. The pH scale highlights the extreme acidity, around pH 2. You can see the bacteria literally breaking apart as they are subjected to this harsh gastric acid. On the right side, we zoom in on a teardrop. Those specialized shapes represent lysozyme enzymes. Notice how they are actively binding to the grid-like peptidoglycan layer of the bacterial cell wall and cleaving it apart. This diagram perfectly captures the immediate, localized sterilization system that works continuously on your body's vulnerable surfaces to keep you safe. We have covered a lot of ground today, so let us summarize the key takeaways. First, physical barriers, like your skin and mucous membranes, act as the castle walls, physically blocking and sweeping away microscopic invaders. Second, chemical and physiological barriers act as the hostile moat, using extreme pH, high temperatures, and destructive enzymes to neutralize threats on contact. Finally, remember that together, these barriers form a comprehensive, immediate shield. By drastically reducing the initial pathogen load, they prevent your more complex adaptive immune system from being constantly overworked. You now understand the vital first line of defense that allows us to interact with a microbe-filled world safely.